And welcome to another physics tutorial. Today we'll be talking about horizontal and vertical projectiles and all the different types of motions that we get in the system. And today we'll be looking at a fairly complicated problem because of some of the dynamics that are involved, but hopefully we'll be able to solve it out, and hopefully this helps any problems that you're having. So let's jump right in. In the figure below, a stone is projected at a cliff of height h with an initial speed of 47 meters per second directed 60 degrees above the horizontal. So the stone is launched projectilely 60 degrees above the horizontal at a cliff h, which you can see over here in the blue, and it hits the cliff at point A. And like what it says here, the stone strikes point A 5.40 seconds after launching. So the stone is hitting point A 5.4 seconds after launching. So let's start with part A. And part A asks, find the height h, so this height, of the cliff. So how do we go about doing that? Well, simply what we need to do is we need to find the vertical height of the system at that point A. And the great thing about this problem is that we're given the time of point A. We know that t at A is 5.4 seconds. So what we can do is we can evaluate a vertical distance equation. But before we do that, let's split this V naught force, if we'll say. We'll label this V naught. Let's split this up into components. So if we split it up into components, what we get is, and let me do this so you can see. Hold on. I'm going to go through the 60 here. But what you get is the horizontal component, 47 cosine 60. And then you get the, and we'll label theta as 60. And then you get the y component, which is 47 sine of 60. So now that we've split up this V naught into different components, we can evaluate our equation. So the vertical distance equation, and I'll just write it here, the vertical distance equation is given by y is equal to Vy naught times t minus 1/2 gt squared. So now we can simply use this equation, and we also know that we're going to evaluate this at t equals 5.40 seconds, because that's when it hits point A, and we'll effectively find the height at that point. So evaluating this equation, we get y is equal to, and we've split it up into this component here. So what we have is y is equal to the vertical component, 47 sine of 60, multiplied by time, 5.40, minus 1/2 times gravity, 9.8, times 5.4, the quantity 5.4 squared. And evaluating that, we get that y of A, or effectively h, is equal to about 76.913226 meters. Alright, so that's part A. So now let's take a look at part B. Part B is asking, find the speed of the stone just before the impact at A. So if you recall, speed is this is a vector in relation to is a vector. It has horizontal and it has vertical components. So in order to find the speed at A, what we can effectively do is we can effectively solve for the horizontal component of velocity, and we can solve for the vertical component of velocity. And that way, what we can do is we can take get the magnitude of that vector, and then we can find the speed. So let's get started. So first, let's write out the component-wise equations. So component-wise, what we get is we get that the horizontal velocity is equal to v naught, which is 47 cosine of theta, and we get that Vy, the vertical component, is equal to V naught sine of theta minus gt. And these equations are simply kinematic equations of horizontal projectile motion, excuse me. So now what we can do is we can solve these equations using our values. So I'll do this in a different color. We get Vx is equal to V naught 47 cosine of 60, which is equal to, this is about 47 over 2. And then I'll do the quantity Vy is equal to, and V naught is 47 sine of 60 minus 9.8 times. And now we're solving this just before the impact at A, so I should also write that t is equal to 5.40 seconds because we're evaluating at A, or just before A, which is essentially A. And so it's times 5.4, and this yields about negative 12.2168. So there we have the vertical and the horizontal components of the velocity, and that makes sense if we were to draw these onto the diagram over here. Here's Vy, it's a downward force, and the horizontal velocity goes this way. So in this system, what we're looking for is we're looking for the speed, which is the magnitude of these two, which is the magnitude of the velocity, or basically the this component here in relation to these two vectors. So we need to take the magnitude of these two vectors. So, and what I'll do is I'll label this as, let's use orange. I'll label this as the speed of A. The speed of A is equal to what we have is the square root for magnitude, the square root of 47 over 2 squared plus negative 12.2168 squared, and this yields about the square root of 701.5, or about 26.48 meters per second. And there we've solved for the speed at point A. So lastly, let's move on to the final part, which is part C. And part C is asking, find the maximum height h reached above the ground. So maximum height h is here, and this is the point, this is the maximum height of the system. So how do we find this? Well, there's a very nice equation derived in projectile motion kinematics, which states that the maximum height of a system is equal to V naught squared sine squared of theta, the initial theta, divided by 2 times gravity. And so, in this case, all we have to do is plug in our values. What we get is, we get 47 squared times the sine squared of 60 degrees divided by 2 times 9.8 for gravity. And evaluating this, we get about, this is about 84.528 meters. And for your convenience, let me just box these in. Here's 84 meters, 26 meters, and then here's the first one. So that's the maximum height of the system.